something very important. We didn't talk about it. Okay, so batch normalization. Yes, batch normalization, it's a technique which is used in machine learning to improve the training of deep neural network by normalizing the inputs to each layer. In fact, it's important because if we do normalization for the input values, for the input features, because it's important and it would improve learning, it should be also, beneficial for each layer if we do this batch normalization for each layer. So the goal of batch normalization is to reduce the internal covariate shift, which is a phenomenon where the distribution of inputs to a layer, it changes during training, making it difficult for the neural network to learn and causing slow convergence. It's typically applied after the activation function of a layer. So after each activation layer, we do this batch normalization for the next layer. It involves normalizing the outputs of the layer over a mini batch of training examples. So we need to select this batch size, for example. For example, if it's 32, for example, and we will get those outputs from each layer, and we will do batch normalization. And after that, we will feed the normalized values to the next layer. It computes the mean and the standard deviation for the layer's output over the mini batch, and then applies a linear transformation to normalize the output. This transformation scales and shifts the normalized output following the network to learn more complex functions. So the batch normalization, it is applied to activation X over a mini batch, right? So this are the steps. So we have X, we calculate X value from activation. So after the activation function, we have those Y values. We will call it here X values. And over a mini batch, if the mini batch size is M, for example, so the input here will be values of X over a mini batch. So it will be X1 until Xm. And we have two parameters here in this batch normalization, which we need to learn. It's gamma and beta, right? So we have those, we have gamma and beta, which we need to learn. And we will work over a mini batch of size M, right? So the output will be Y. It will be this batch normalized or batch norm of Xi over gamma and beta, right? So first, we have those first 4 steps. First, we need to get the mini batch mean. So over this mini batch, we need to calculate mu. So mu, it will be 1 divided by m of the summation of xi, for I equal 1 to m, for example. After doing this mini batch mean, we will do this mini batch variance. So for each xi, we will subtract xi from mu and square it, take the summation and divide it by m to calculate this variance. So it will be mini batch variance. So first we calculate this mini batch mean, and after that we will calculate this mini batch variance, correct? And take the square root of no, it will be, we will do normalization. So we will normalize each xi. So it will be xi minus mu beta divided by square root of the variance, or divided by standard deviation, because the square root of variance, it's a standard deviation. So we will get this normalized outputs. After that, we will do some scaling and shifting. So each x normalized, we will multiply it by gamma and add a beta to it to try to do some scaling and shifting, right? To get yi. And after that, we will feed this yi to the next layer. So we will do this over each mini batch. So for each layer, we will apply the inputs. We will calculate the outputs after the activation. So we will get those x values over the whole mini batch. So we'll apply for the mini batch. We will do this one layer by layer, right? We will do this one layer by layer, and so instead of feeding x directly to the next layer, we will feed yi, and yi it will be gamma multiplied by xi normalized plus beta. Those gamma and beta, it's trainable parameters. Mean and variance, it's non-trainable parameters, which we need to adjust by calculations. So those 2 parameters, it's non-trainable, it's by calculations. But gamma and beta, it's by training. We need to include those 2 parameters in the optimizer, right? So it will be one layer. In fact, when we need to use batch normalization, we need to add batch norm layer. and this batch norm layer, it will be after activation. So this is a model, for example. So I apply the input. Of course, we need to normalize the inputs. So we'll have here some weighted sum omega x plus p. We will use some linear function or some nonlinear function. Sorry, this is a linear part, omega x plus p. We will calculate this weighted sum. It will be z, for example. We'll apply this to the activation function. We will calculate a, for example, and after that we will apply this a to batch normalization. We will get bn, for example, and we will feed this one to the next layer and so on. So instead of feeding this number directly to this layer, we will have this in between batch normalization layer, and this batch normalization layer, it will try to normalize the outputs from this activations, from the previous activations, before feeding it to the next layer. So the job here, batch normalization, it's another network layer that gets inserted between a hidden layer and a next hidden layer. We will insert it between one hidden layer and the next hidden layer, and its job is to take the outputs from the first hidden layer and normalize them before passing them into the next hidden layer. And each batch norm layers has 4 parameters, as we described before, 2 trainable parameters, which called the beta and the gamma, right? We need to train beta and the gamma, and the 2 non-trainable parameters, which is a mean moving average and the variance moving average. So we need to calculate this mean and variance. We calculate mean and variance, and we will store those 2 values, and trainable parameters, which is beta and gamma, right? And this process here in each batch norm layer, it will receive those activations from the previous layer, and it will do batch normalization before delivering it to the next layer. During the training process, we feed the neural network 1 mini batch of time at a time. So we feed the network 1 mini batch of data at a time. Each time we will feed it by mini batch, and during the forward pass, each layer of the network processes that mini batch of data and pass that as an input to the batch normalization layer. So first, we have our mini batch. We will pass this mini batch to the first layer. We will get those outputs. We will send those outputs to this batch normalization over, and it will do those calculations over the mini batch. So in this case, it will calculate this mean and variance. It will calculate mean and variance, and it will try to learn those 2 parameters over different epochs. So it will calculate mean and variance, and maybe in the first epoch we will initialize those beta and gamma by random values, and it will try to adjust to those beta and gamma over, each epoch, for example, in each iterations. And it will send this batch normalized values to the next layer, and in the next layer we will have also batch norm between this layer and the next layer, and so on, right? So in each batch normalization layer, we will do those calculations. We will calculate mean and the standard deviation or variance. So we will calculate those 2, mean and standard deviation. We will do normalization. So it will be a or feature a, for example, or input minus mu divided by standard deviation. And after that, we will do scaling and shifting. So the batch normalized output, it will be gamma multiplied by a plus beta. Gamma and the beta are trainable parameters. So we will do this one in the forward pass. Okay. And in fact, and after that, we will calculate mu and the sigma, those mean moving and the sigma moving, and we will keep it for inference, right? Because in the training process, we will do this process in the training. We will do those calculations in the training, but in the inference, and when we are testing our model, we don't have any training, right? So each time, in fact, we need to use this mu and the sigma, so mu and the sigma, and try to update this mu moving average and the sigma moving average, right? Moving average, mean and variance or standard deviation, and we will do this updates, and we will keep it for the testing phase. So in fact, when we in this batch normalization, it has 2 phases: one phase in training and one phase in testing. In training, we will do those calculations in forward pass, but each time also we will try to update mu moving average and the sigma moving average, and we will store it. We will not use it, but we will keep it for inference or for testing. So during inference, we have those numbers stored, right? We will have this mu moving average and the sigma moving average. So we will use those values which we stored before, and we will use it for doing normalization. So we'll apply some feature input features. We will use those mu moving and the sigma moving for doing normalization. And after that, we will do scaling and shifting using gamma and beta, which we have already during the training process. So in this case, we will calculate the output batch normalized. Batch normalization layer process its data as follows in the activations. Activations from the previous layers are passed as input to the batch norm. One activation vector for each feature in the data. Mean and variance, we will calculate for each activation vector, we will calculate mean and variance of those values in the mini batch. And we will do normalization. So it will be x minus mean divided by standard deviation. We will calculate normalize the values for each activation vector using the corresponding mean and variance. These normalized values now have zero mean and unit variance, for example, unity variance. We will do scaling and shifting using gamma and beta. And after that, we will update this moving average, mean, and variance. Step number 5, it's just for inference, right? We will not use it for the training process, but we will use this one for testing, for example, when we are testing or when we want to do some, when we deploy the model in real time. Benefits of batch normalization. Deep neural network can be trained faster using batch normalization. So although each training iteration will be, because now we inserted a new layer, batch normalization layer, so we should expect that the training process will be slower, correct? So because we do more calculations, because we added extra layers, so we should expect that it will be slower, but the performance in the training will be much better. So the model maybe will converge faster, but each iteration will be slower. It's very important to note this, because we added this batch normalization between each two hidden layers, for example. So we should expect that we will do more calculations. So the whole process will be slower, but the model will be trained faster, right? So maybe instead of getting your model converged in 100 epoch, maybe using batch normalization, maybe it will converge into 50, for example. So the model will converge faster, but the calculations will be slower. Higher learning rates, gradient descent generally requires a small learning rates for the network to converge. So as network become deeper, gradient becomes smaller. Anyway, when you are using this batch normalization, you need to use less learning rates. Sorry, higher learning rates without risking overfitting. And it's easier to initialize weights. Those are the advantage and the disadvantage of this one. So now I have this MLB for iris dataset. If you can remember iris dataset, it's a dataset where we have 150 samples, and it should be classified, each example should be classified into one of the 3 classes. So I need here to define a simple neural network with batch normalization layer. So the first dense layer, it will be ReLU, 32 units here, which means input shape, it will be 4, because if you can remember the iris dataset, it has 4 input features. And target feature, it's one of the 3 classes. So I will use ReLU. I will use here batch normalization between the first dense layer and the second dense layer. So I have here batch normalization. The second dense layer, it has 16 units. It's ReLU also. And the output layer, it will be 3, because we need to classify each example into one of those 3 classes. So I used here batch normalization between each 2 hidden layers. If we need to calculate number of parameters here, the first hidden layer, number of parameters will be 160, which means it's 4 times 32 plus 32, right? So this 160, it's a 4 input multiplied by 32 plus 32 equals this number, right? So this is the first dense layer. The batch normalization, I need to know how many parameters here in this batch normalization, right? We'll do this batch normalization for each input feature. I have 4 input features, right? Correct? For the input features, but how many input features are coming from this dense layer? It's 32. The input features are 4, but the number of outputs from this dense layer will be 32. And for each input, because I need to do this batch normalization for each input, and for each input, we understand, from the first slide, we know that each batch normalization, we will have 4 parameters, 2 trainable and 2 non-trainable, correct? 2 trainable and 2 non-trainable for each input. So in this case, number of parameters in this batch normalization layer here, it will be 4 times 32, right? 4 times 32. Out of those 4, we have 2 trainable and 2 non-trainable parameters. So in total, it will be 128. Those 128 should be divided by 2. So it will be 64 trainable, 64 non-trainable, right? The second dense layer, when we do batch normalization, number of output shape will be the same, but it's just batch normalized. So the input shape will be 32, the output shape, it will be 32, but batch normalized. So number parameters of this layer, it will be, we have here 16 units. So it will be 16 times 32 plus 16, right, to get this number. So this number, it will be 16 times 32 plus 16 to get this number. This layer, it's followed by batch normalization. Number of inputs to this layer, it will be 16, right, times 4. So number of parameters here, it will be 16 times 4. Out of those 4, 2 trainable, 2 non-trainable. So in total, it will be 46. 32 trainable, 32 non-trainable. So the total number of parameters here, it will be 933. But remember, because we have trainable and non-trainable, right? So from those 931, we will have 835 trainable and 96 non-trainable. Those 96 are 64 and 32, right? Just summing those two together, it will be 69, right? Oh, sorry, 96 non-trainable. So it's just to understand, I mean, the meaning of those numbers. If you got those numbers, it should be easy for us to understand those numbers. So now we will train the model. I trained this model with batch normalization and without batch normalization. So, and I calculated the runtime. So as you can see here with batch normalization, the runtime is higher. In case without batch normalization, it's much faster. In fact, the runtime, correct? I trained this model for 200 epoch, but as you can see here, we converge it faster. I mean, the runtime here, it's much higher because we have two extra batch normalization layers. I mean, in this model here, we have 2 extra batch normalization layers. So we should accept, and we have more parameters. If I will remove those batch normalization layers, number of parameters will be much less. So the model will train faster in 12.7 seconds, but with batch normalization, it takes more time I mean, calculation time will be much higher. But as you can see here, the model converged faster. We converge it here at 175 epoch. We converge it here maybe at 90, for example, or something. So the model will converge faster. But at the end, we will have the same accuracy. So this is the confusion matrix for the test set. This is the confusion matrix for the test set. This is the classification report. So almost we have the same numbers, almost the same numbers exactly, right? Yes, so if you want to go to the example in GitHub, you have this link. You can go to the example and you can run the example and try to dig deeply into it. Yes, any questions for batch normalization? Any questions, please? So batch normalization is very, very important. I mean, also because also we use this maybe if you use RNN, it will be smart to use batch normalization, and it will be smart also to use drop out. It's very, very important. So just remember to use those in your model. Yes, any questions, please?
No question on my side.
Okay, so thank you very much. So I guess today we are done with today. We finished this batch normalization. We still have maybe some time. I just have 2 slides. One slide for this one-shot learning, and the other one it's for transfer learning. And in transfer learning, it's very simple because it's just I try to explain, present some models which can be used in transfer learning, like AlexNet and ResNet and stuff like this. So what we need to finish now? It's this one-shot learning. It's short slides. In part number 8, you can go through it by yourself if you want, but maybe we can have also another week where we can finish this transfer learning part and this one-shot learning and a few shot learning and 0-shot learning. It would be nice. And after that, we finished. So, I mean, we covered the many stuff this semester, but it's nice because it's good knowledge, and you have the slides in Blackboard. If you would like to keep it, for example, we have those links also for those videos if you want to go through this one before. And please just feel free to send me any questions, or if you have any questions, just ask me. We will not have lectures next week because I have a special meeting in some place, so I will not be available this Friday. But the next week, we should have a meeting and try to finalize and conclude. And maybe after that, we can have 1 week for presenting, for you to present your results. And after that, we will have maybe some weeks off until you submit your final report. So again, please try to write your report as a paper in the paper format. So it will be easy for us to read your results. We will assess, all sections of a paper, for example, if you are sending it to a conference or a journal. So it should be something which is publishable. But don't worry about this. If you don't have enough time, try to focus on the results, which is very important, but try to put it in this paper format. So after finishing the course, you can get and try to update it, for example, and you can publish it. So it will be very good production from the course. So thank you very much for today, and let us meet after 2 weeks.
Thank you all. Have a nice weekend.
Thank you very much. And please just don't hesitate to contact me if you have any questions. And please, for the reference group people, please try to send me your report, please. It's just I'm asked to send it to the people here, so it's very important to send it to me, please. Thank you very much for today. Yeah. Thank you.
Thank you,
Professor, is there any deadline for the reference group by which date we should submit?
Because we should have 2, in fact. We should have 1 in the middle. So
Okay.
it's too late for the 1 in the middle. And we should have 1 at the end, after the exam. So the same group, please, I wish to get 2 reports from them, 1 in the middle, 1 at the end.
Okay, fine. I'll send it.
Okay, thank you very much. Have a nice weekend.